Hi, this is ET370, Lecture 13, Part B, and here we're just going to talk about full and half adders. All right, this is how a computer can take binary numbers and add them up. All right, so the first one we'll look at is a half adder, and there's two inputs, and it's A and B, and these can be 0, 1, or 0 and 1, and the output will be a sum and a carry bit. Okay, and this is the idea of how it works, right? If you were to sum, the bits here, what do we have? Nothing. I have one. I have one, and then I have two. Now this is a base 10 number, and so if we're in binary, we don't want to deal with that. We want base 2, and so this is what we want: 0, 0, 0, 1, 0, 1, and 10. Remember, 1 plus 1 is 10. Okay, so if there's 2 bits here, we want that to be represented with 10. Okay, this is the sum bit. This is the carry bit. Okay, and so this is essentially 0 to 2 in our base 10. Now the circuit that we're going to use to implement this uses an AND and exclusive OR. All right, and so what do we have? We have an AND here: 0, 0, 0, 0, 1, 0, 1, 0, 0, and 1, 1 begets 1. Good. Exclusive OR, we have the output is only true when only one of the inputs are true. Okay, as opposed to here where all you need everything to be true. Okay, so let's look at the implementation of a half adder. So this is what it looks like. You have just an AND and exclusive OR. Boom, right here. And notice the input A is going to both, and so is the input B. Now the output of the AND is the sum bit, so that's this one, and the output of the exclusive OR is the carry bit. And let's just walk through what's going to happen when we activate the 4 cases of the truth table. Okay, so if we have 0, 0, right? So this is 0 and this is 0. What's the output of an AND? Well, the output of an AND for 0, 0 is going to be 0, and the output for an exclusive OR is also 0. Okay, so that's pretty straightforward. Good. 0, 0, and you'd have 0, 0. Fantastic. What about if we had 0, 1? Okay, so B is 0 and A is 1. Well, this is still 0 because anytime you AND something with 0, it's still 0. But this is an exclusive OR, and that'll be 1. So you're left with this. That's good. Now, if you flip it so that B is 1, or A is 1 and B is 0, right? It's going to be the same result, right? Because either way, you're giving a 1 to the exclusive OR, and here for the AND, you're giving a 0. So this is definitely zeros here. Now, the last one, if you put a 1 and 1, well, the AND is going to be 1, and the exclusive OR is going to be 0, and that's how you get the 10 or the 1, 0 here, which is equivalent to 2. Okay, and so this is an implementation of a half adder, and we can go to Circuit Sim and check this out. So let me do that. Let me switch screen here. So share screen 2. And again, you can see here that there's a AND and an exclusive OR. And if you go to the Falstad simulator, you can always go to combinational logic and hit half adder, and it'll pull up this example. And if I run this, notice I have 0, 0. And if I hit 1 here, notice it goes 0, 1. Good. Also 0, 1. Right? But if I do 2 bits active, then it gives me the sum of these 2 bits, which is 10, right? 1, 0. So this would be a way to implement an addition circuit, a half adder, in binary. Okay, so let's go back to looking at a full adder. So a full adder, if I stop, yep, there we go. A full adder looks like this. Let me go over the intention first, and then we'll go over the circuit last. Okay, so it takes 3 inputs, right? And so here's a 3 input binary sequence: 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. And just to remember for binary, if you can look at the first, second, and third columns here, you alternate every 1, every 2, and every 4. That's the pattern. That's just another way to double check. Okay, so what's the intention for this one? Well, if I have three inputs, if any one of these are active with only 1, I should only see 1, right? If any of these have 2, I want to see 2, and any of these have 3, I want to see 3. So let's look at this for a base 10. So only the last row has 3 here, whereas this one has 1, 2, yep, 2, 1, 2, 2, yep, 1, 2, good, 1, 1, 0, good. Which means this should be 0, 0, This should be 0, 1, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, and 1, 1, because 1, 1 is the same as 3 in base 10. Yep, good. Okay, so this is what we want to see. So it's still only a 2-bit output, but now we have a 3-bit input, and we can go up to 3, whereas this one you can only go up to 2. So 0, 1, 2, where this can go 0, 1, 2, 3. Okay, so let's look at how this is implemented. And it looks a little crazy. What do we have here? We have an and exclusive or, right? We know what that is. That looks very much like a half adder. And you have another and an exclusive or, and another or here. So you got a half adder, and an or right here. Interesting. Okay, so the A and the output of this is going to this half adder, and the B and C are going to this kind of half adder looking like thing, right? Okay, so what can we do? We can prove this to ourselves by building out a truth table. The same truth table, 0, 0, 0, and all the way through, right? I'm not going to go through that again. But look at this. I have outlined here X, Y, Z. What's X, Y, Z? X is going to be the output of the AND for B and C. Good. Y is going to be the output of the exclusive OR between B and C. That's fine. Z here is the output of Y ANDed with A. Good. And what do we have here? S is going to be the output of X ORed with Z. And C is going to be A exclusive ORed with Y. Okay. And then finally, we can verify, is this predicting the same thing as this truth table? Are we getting the same intention? So let's work it out. So let's do X. X looks at just B and C and ANDs them together. So we should see 0, 0, 0. Yep, good. Both are true. 1, 0, 0, 0, and then 1. Excellent. Okay, Y here is the exclusive OR between B and C. So I believe we should only see 1 here, 1 here, 1 here, 1 here. Perfect. 2 1s, 2 1s. Okay, let's look at the next one, Z. So Z is here. So now that's looking at A and Y. And I hope you're seeing that I can methodically walk through this and convince myself of the final output. So Z is A, which is this column, and Y over here. So I'm going to AND those two. So no, 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 no. Yes, right there. Good. Yes and no. Excellent. Okay. And then the last thing is S and C. So S is the OR of these two. So if I look down carefully, yep, ping, that should be it. And yep, that's one. Yep, another one. And that's another one. So here, 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 and here, right? Okay, and the last one, C, the carry bit, is the exclusive OR of A and Y. So what's A, and Y? That's these two. And so I go exclusive OR, yes, 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 no, no, yes. Boom. Yes, yes, no, yes, no, no, yes. And I can always verify. Look at this. Zeros, 1, 1, 2. Yep. 1, 2, 2, 3. And that should match our desired table. Double check. 0, 1, 1, 2. Yep. 10, 0, 1. Yep. 1, 0, 1, 0, 1, 1. Perfect. Okay, so this is an implementation. And this very last thing, we're just going to check it on the circuit sim and verify that it meets our requirements. So go to screen 2 here, circuit sim. And again, you can go circuits, combinational logic, full adder. And this is the same circuit. I'm going to run this. And look at this. If I turn any one on, I see a 0, 1. So I turn that off. 0, 1, 0, 1. Good. If I turn any 2 on, I should see a 1, 0. Good, 1, 0. If I turn these 2 on, good, 1, 0. And if I turn these 2 on, 1, 0. Perfect. And then the last one is 1, 1, 1, and boom, we get a full adder behavior right here. Okay. All right. Well, I hope you learned a lot. And this is a way to implement binary addition in the computer. Okay. And so that way it shows how the computer can do some cool calculations. All right. I'll see you in the next lecture.